Chapter 2 is Descriptive Statistics, and we will go through all of these sections. Before we do this, let's go through the why slides, which explain the rationale behind what we did last week. So last week we discussed study design for collecting data. So why did we do that? Because the data collection step is of fundamental importance in research study. If your data collection is flawed, the whole study is flawed. Remember the garbage in, garbage out? That's what this says. And we introduced two particular designs for collecting data: observational studies and experimental designs. Why? Well, for observational studies, the individuals are just observed and the variables of interest are measured, but there is no attempt to influence the responses. In contrast, for experiments, some treatment is deliberately imposed on individuals, and then we observe their responses. So why would you do an observational study? Well, from observational study, we can find an association between two variables. So for example, if you didn't know it was there, you could look at existing data and explore it to try to see if you see any association, and then maybe you would want to go further. But you need to be careful. Association does not mean causation. And maybe you remember the example of the heat stroke and the ice cream sales. So that explains why we sometimes want to do an experiment. So an experiment allows us to demonstrate causation. So maybe the observational study revealed an association which made you suspect causation, and the second step would be to run an experiment to demonstrate that. So it allows us to demonstrate causation because we can make an intervention, so modify the cause, fix the other variables, and see whether the change in what we suspect to be the cause indeed has an effect. So to run a good experiment, we need to follow a few principles. We need to compare, which means we need a control group to which we'll be comparing, and this protects us from lurking and confounding variables. We need to randomize when we allocate people to group in order to remove selection bias. We need groups that are large enough, so we need to repeat on a quite large number of individuals, because there will be variations between people which are due to chance. The people are different, so we want to reduce that. And finally, if we think there is something going on, in order to be totally sure, we need to replicate the experiment and redo everything in order to reduce the problems due to errors and bias. So what's the plan for the next two sections? Well, numerical and graphical summaries for one variable are mostly revision from high school, so we don't need to go through all of the slides in lecture. Nevertheless, we wanted all the content to be in the slides, so you would not know to go look for it on the internet or wherever, especially since everybody seems to think they can write about statistics, and so what you find is not always very accurate. So in class, we will cover what you may not know or what you haven't thought of. So a few things. So we will review the table of frequency, the difference between means and median, and the different measures of spread. We will be talking about RStudio, which is a statistical package we'll be using in this course. Or question, why do we want to use graphs when we could be using numbers? This kind of fundamental questions. And we will show that the mean is the center of gravity of the data. We'll not really show it, we will illustrate. And then there will be slides we don't really talk about. So they will be called reference notes, and that means you can come back to those. For example, there is a rule that tells you what is a suspected outlier, and there's not much point in me telling you now in a video, because that's exactly what I'm telling you in the Mobius lessons in a video format. So it will be the same person saying the same thing. Let's look at numerical summary for one variable. Numerical means we want to summarize what's going on by a number. So in this section, we'll look at common types of numerical summary of data, right? So that's way of summarizing the key properties of data using numbers. Numerical means numbers. So the learning outcome from section 1. We want to learn to describe one categorical variable using numbers. And we want to understand how to summarize one quantitative variable using measures of center and measures of spread, and understand what outliers are and how they impact what we have. And so It would be a good idea if you could use those once you've watched the video and think you understand, just to see if everything in there and you can actually tick that. This little table is going to follow us and we're going to fill it with times. For now, we have one variable and we want to summarize it using numbers. And as you can see, what we do depends on whether it's categorical or quantitative. So the numbers we use to summarize things depend on the type of variable. And as you can see, they also depend on the number of variable. So for now, just summarize by numbers. There is only one variable. So exploratory analysis is what you do at the beginning. You get a set of data and you want to get a feeling for what's going on. At this point, you don't remove any data, you just look, right? You explore what you have. So you're trying to describe the main features of the data set you have. And one way to do this is to use numerical summaries. And you know a few of those. You can find some proportions. So what's the proportion of observation which have this or that characteristic, or the percentage? You can calculate the mean or average, that's the same thing. The median of your data set maybe. The interquartile range. If you don't know what that is, we'll get to that. And you can measure the standard deviation, which measures how spread your data is, right? So this number help you understand what's going on. Finding the number and stopping there would not be very helpful. So that's when you want to summarize by numbers. When you want to summarize using graphs is something we'll talk about later. So let's talk about the statistical distribution of a variable. It's a list of two things. It's really the set of all possible values of that variable. And then for each possible value that counts, as many times do we get this value or that value. And for quantitative variable, for example, travel time, we could count the number of values falling in some predefined range. So for example, if you're looking at travel time, you could put like in just together all the travel time between 0 and 10 minutes, and then all the one between 10 and 20 minutes, for example. Let's see what we have for one categorical variable. So in this example, we're looking at the MATH1041 class survey. And the question was, did you watch the Australia Open Women tennis final? Yes or no? So there are only, so did you watch would be the variable. There are only two possibilities, yes or no. They're not expressed by number. So basically we have two bins. And so people go either in the yes bin or in the no bin. And so that's a categorical variable. And one way to summarize what we have would be to use frequency. So that's when we count, or percentages. So that would be a way to summarize this variable, which is categorical, using numbers. And in fact, we're not losing much there. The only thing we're using is who said yes and who said no. So that was an example. And the general case is the same. So if you want to numerically summarize a categorical variable, you will use what we call a table of frequency, which is basically what we had on the previous page. You will have a list of all the possible categories in a table of frequency for a categorical variable. Even if they were not observed, you write whatever is possible. And then for each of those possible values, you will write the counts as percent or proportion. So just something about the vocabulary. When we say percentage, for example, if you have 25%, what we call percentage is the 25. We've been discussing numerical summaries for a categorical variable, but probably from the back of your mind, you remember from high school that we were using other numbers to summarize what was going on. We're calculating the median. So there is the mean, the median, the quartiles, the 5-number summary, the standard deviation. Could we use those to summarize what's happening with our categorical variable? You can think of the example if you'd like. Why or why not? I'll let you think about that because it's going to help you know what tool works in which situation. The answer is no, these don't make sense for categorical variables. If the only possible answers are yes and no, how do you average yes and no? So these don't make sense for a categorical variable. So for categorical variables, we'll have to stick to our table of frequency. But your memory was correct. These exist. They make sense for, remember? They make sense for quantitative variables, and we'll be using them. So if we want to describe a quantitative variable using numbers, we want to describe two things basically. The center, the location, where most of the data are, centered around something, and then the spread. And we can do this using numbers. So you expect that we're going to need two numbers because we want to describe two different things. Let's look at the measures of location first. So given a measurement of a quantitative variable, an obvious question is, how large or small are the values on average? And the measures of location tell you that. So if you consider, for example, the class survey, one of the questions was, what is the satisfaction rating with UNSW on a scale from 0 to 10? And the mean satisfaction rating was 7.35. This was the mean. So how was this calculated? See here it says reference note, so it means I don't need to re-explain to you. You can look by yourself. So I just say you add all the values and you divide by the numbers of value. You knew that. Let's look at another example. A small company employs 4 young engineers who each earn $70,000, 2 senior engineers who earn $88,000, and the owner, who's an engineer also, and who gets $160,000. The latter claims that on average, the company pays $88,000 to its engineer, and then it's a good place to work. Do you agree with this claim? First, you can redo the calculation, and it's true that if you calculate the mean of all those numbers, you will get that. So that part of the claim is correct. That's really the mean in this company. Nevertheless, do you agree with the claim? Another good time to pause the video, and maybe another time also to think about, you know what you want to measure. Have you been using the best tool to do that? Well, what you can see is that the average has been pulled up by this number, which is much bigger than the others. And if you're wondering, as an engineer, if it's a good place to work, probably you wouldn't be the boss, so you don't want this to influence the calculation too much. So there is a better tool than the mean to calculate that, and it's the median. The median would be the value in the middle of the observation, if you'd like. It's 70,000, and that's a much better representation of the amount of money you could earn if you work there. It's not as sensitive to the outliers as the median. So that's why sometimes it's a better tool. So how do we compute that? Basically, you take your values and you split them in half of the values below, half of the values above. And this is a bit of a reminder of how we do it. It's going to depend on whether the number of values you have is even or odd. That's called reference note. That means that thing you've learned earlier and that you can review in your own time. Mean versus median. Why? Basically, if we had the mean, why did we have to come up with the median? The main reason is the outliers. These are values that are unusually large or small compared to what you expect to have, and so they're quite far from the bulk of the data. And if you have one such value which is much bigger than all the others, it's going to change the mean a lot, whereas it's not going to affect the median as much, and the median might give you a better idea of what goes on. One of my favorite examples, just to convince you that the mean can be grossly affected by outliers. In fact, it can be so effective that it can be meaningless. So can you think of an example where knowing the mean gives you almost no idea of what's really happening? I will give you a bit of time. And so by definition, the median is in the middle of the data. Basically, half of the value are below, half of the values are above. The mean doesn't have to be like that. Can you think of an example where most values, and in fact, maybe 99% of these values would be above the mean? Yes, that can happen. The goal of this example is to convince you that although the median has to be around the middle, the mean really doesn't have to. Pause, think, come back. Well, when Bill Gates enters a bar, on average, that's the mean, everybody in the bar becomes a millionaire. But it tells you absolutely nothing about the wealth of the people who were already there. This outlier, which is going to be Bill Gates' revenue, is going to basically erase all the rest. So that's the only information that's left, and that's an example of a really large outlier, which makes the mean meaningless. Now let's look at an example where the mean is not at all around the middle of the data. Almost everybody has an above average number of legs. Yes, you can imagine that someone had an accident or something, so not everybody has 2 legs, but so the average number of legs of people on the planet would be 1.99999, and 99.99999% of people have 2 legs, so they have a number of legs which is above average. So the mean and the median are quite different. The quartiles, that's again a reference node. Basically, it's going one step further than the median. The median was used to keep the data in half. So Q2 really is the median with 50% below and 50% above. And as you cut again, quartile, so you make quarters, you're trying to divide your data into 4 sets of equal size. So reference node again, which gives you precise definitions. And then you also, it tells you how to calculate the quartile. So please, if you're not sure, look at that. There's also a video about that in the weekly Mobius lessons. And really, so different people can do it in slightly different way, which is very annoying because when you use different software or different commands inside the same software, you get different values for the quartiles. And I say it's annoying when you have a small data set, but usually if you have a small data set, well, really, you can get a feeling of what's going on. So you don't necessarily calculate summaries. And when you have a very large data set with thousands of values, all the calculations for quartiles of median are going to be giving the same thing. But really look at how R does it, because we're going to be doing it the same way. Again, read those in your own time and look at the Mobius weekly lessons. So the mean and the median, we're trying to give you an idea of where the values are, so location, where they are. Now we also want to measure how spread the values are. It's important because, for example, you can imagine 2 countries which would have the same median income, whereas in one of them, almost everyone would have the same income, more or less, and you could have that median in a country where the rich are really rich and the poor are really poor. So you need to know a little bit more than just the location to get a feeling of what's going on. I'm sure you'll know several measures of spread. So one is the interquartile range, which basically tell you where the 50%, where the central 50% of your data is. The interquartile range is a number because you get it by calculating 3rd quartile minus the 1st. So basically what you are calculating is this distance here. Interquartile range. So that's one you can use, and because it's dividing the data into these four sets with the same number of value, it's not going to be affected very much by outliers. Whereas the usual one, the most common one, is the standard deviation. And the standard deviation, so what you do, so basically you're trying to measure how far things are from the mean. So you take one number, you subtract the mean, and then you square. Take the second value, subtract the mean and square, and so on. And then if you're in a sample, you divide by n-1, and finally you take the square root. And so that gives you the standard deviation. Of course, because it depends on the mean and because it takes the values one by one, not just their order, it's going to be affected by outliers also. We really never or very rarely calculate this by hand. We have software to do this for us. So that was the standard deviation. We also use the variance, but the variance basically has the same information as the standard deviation because it's just the square of that. So if you denote the standard deviation by S, then the variance would be S squared. Calculating standard deviation and variance by hand using the formula can be really tedious, especially if you have a lot of data. So fortunately, we never do this. So in MATH1041, we use RStudio. It's possible to do it with a handheld calculator, but it's really complicated. It takes time. And then people always make mistakes when they input the data. but it's possible using the statistics mode. I would not recommend it. The 21st century of calculating a standard deviation, if we assume that those are the satisfaction score with UNSW, would just be to use the command SD for standard deviation. And the way to calculate the mean, again, we don't do this by hand. So we put all our values in an R object, which is going to be called a subset. This is for combine. And then we can calculate the mean of this subset and the standard deviation of this subset. This C here is just to ensure that these two numbers will be on a single line, so it displays a little bit better. So which numerical summary should you use for only one variable, which is quantitative? The ones which are commonly used for location, usually people use the mean, and for spread, they usually use the standard deviation. But if there are some outliers, that can be a bad idea. So in those cases, you turn to the numbers which are robust to outliers. So for location, you would use the median instead of the mean. And for the spread, if there are outliers, then you would use the interquartile range instead of the standard deviation. And I would say if you need to explain to people what these numbers are, it's clearly much easier. So that's another reason to use them. So 5-number summary is a way to summarize what happens with a one quantitative variable using, well, guess what? 5 numbers. And that's explained in the online tutorial, which are now called the weekly lessons. So I will just let you watch that video because otherwise it's going to be the same person saying the same thing. So there's really no point. We have these two commands. One is called summary. The other one is called 5-number summary. And the 5-number summary will give you 1, 2, 3, 4, 5, which are exactly the numbers you want. So first quartile, the median, and then the third quartile. Whereas summary will give you these numbers, and it will give you also the mean. So it's important that at the end of a section, you try to reflect on what you learn. And it's a little bit like the checklist initially, that there are different types of variable, and that really tells you what numerical summary you're going to use. You should also know by now what are the possible numerical summary when there is only one variable, depending on its type. And you should know using R how to calculate the location and the spread using numerical summaries, using RStudio. And the limitation of those tools, and in particular the fact that the mean and the standard deviation will be very sensitive to outliers. Keyword, never move on before you for sure know what all these mean.